Okay, these are the answers to the practice quiz on measurement and unit conversions. For numbers 1 through 5, you have to select the official SI base unit for that particular quantity. And here is the list of SI base units that you should memorize. So for mass, it's the kilogram. Length, it's the meter. Time, the second. Amount of substance, the mole. And temperature, Kelvin. So number 1, amount of substance is the mole. So that's J. For length, it is the meter. That's G. For mass, it is the kilogram. That's E. Temperature, Kelvin, D. And then finally, time, the second, M. In number 6, you have to determine the number of significant figures for each measurement. Let me remind you about the Atlantic and Pacific rule. First, if a decimal is absent, you should start counting the digits from the Atlantic Ocean side of the number, which is the right side. Skip over any zeros on that side and begin with the first non-zero digit and continue counting every single digit from that point on until you reach the end of the number. So as far as the Atlantic rule, where a decimal is absent, our second entry in the table says 25,000 meters. Since a decimal is absent, we start on the Atlantic Ocean side of the number, skipping over the zeros, and because all we have is the 2 and the 5, that measurement has 2 sig figs. The only other measurement in which a decimal is absent is 12,500 kilograms. Again, starting from the Atlantic Ocean side of the number, the right side, and skipping over those trailing zeros, we have 3 significant figures. Okay, now let's talk about the Pacific rule. So if a decimal is present, you should start counting the digits from the Pacific side, or the left side of the number. Again, skip over any zeros on that side of the number. Begin with the first non-zero digit, and then continue counting every single digit from that point on until you reach the end of the number. So our first measurement, 32.00 milliliters, has a decimal present. So we start on the left side, the Pacific Ocean side of the number. The first number we come to is a 3. So everything counts from that point on. That measurement has 4 sig figs. Next example, 9.001 seconds. The first number we come to is a 9, and everything counts from that point on, so also 4 significant figures. But now we have some leading zeros, 0.0650 grams. We skip over those first 2 leading zeros. Once we come to the 6, everything counts from that point on, all the way to the end of the number, so that has 3 significant figures. In our next example, we skip over the leading zeros, so we only have 1 significant figure. Now we have skipped over the first 2 zeros, 0.050 moles. Once we get to the 5, we count from that point onward 2 sig figs. And then finally, 87.0 Kelvin. The first number we come to on the Pacific Ocean side is an 8, so everything counts, 3 sig figs. Okay, for number 7, you're going to be creating a conversion factor to convert from one unit to another, and you'll have to know your metric prefixes to set up that conversion factor correctly. Make sure that your conversion factor is clearly labeled with a number and a unit on both sides of the horizontal line. Make sure that your final answer has a unit. Make sure that your final answer is expressed with the proper number of sig figs, and expressing your answer in scientific notation may be convenient in some cases. So for this first example, they began with 298 micromoles, which has 3 significant figures. They multiplied by a conversion factor that puts micromoles on the bottom and moles on top. So the final answer has unit of moles. And it turns out there are 1 million, or 10 to the 6th power, there are 1 million micromoles in 1 mole. So with the calculator, you would take 298 divided by 1 million. Now the answer you get is 0.000298, which you could write in scientific notation as 2.98 times 10 to the negative 4. Again, that number also has 3 significant figures. So now let's take a look at our first example. Convert 0.0570 kilojoules into joules. So the capital J just means joule. It's a unit of energy. That's not really important that you know that, but the fact that it's a kilojoule versus a joule, we know that the metric prefix kilo means 1,000 times the base unit. So we start with our number, 0.0570 kilojoules. Then we do our horizontal line. This is our conversion factor. We know we're going to put kilojoules on the bottom and joules on top. We know from our knowledge of the metric prefix kilo that 1 kilojoule is equal to 1,000 joules. So 1 on the bottom, 1,000 on top. This means that our answer will come out in joules. Now we have 3 significant figures for the initial measurement because those first 2 zeros, those are leading zeros, they don't count. Our answer should have 3 significant figures, but when we do this on the calculator, 0.0570 times 1,000, our calculator only gives us a number of 57. This is only 2 sig figs. If we need our answer to be 3 sig figs, we have to express it as not 57, but 57.0 joules. And this is 3 sig figs, and that is our final answer. Okay, let's take a look at the next problem. Convert 7.0 milliliters into liters. So we start with 7.0 milliliters. We do times and draw a line. This is our horizontal line for our conversion factor. We're going to put milliliters on the bottom and liters on top. Our knowledge of metric prefixes tells us that 1 liter is larger than 1 milliliter. So how many milliliters are in 1 liter? Well, the prefix milli means 1,000th of the base unit. So there are 1,000 milliliters in 1 liter. So 1 on top and 1,000 on the bottom. And if we do this math, we should get our final answer is supposed to have 2 significant figures. When we do 7.0 divided by 1,000 on our calculator, we get 0.007, but that number only has 1 sig fig. If we need 2 sig figs in our answer, we must express this answer not as 0.007, but rather 0.0070. The leading zeros do not count, but the 7 and that final 0, those are the 2 significant figures in this final answer. And now on to part D. Convert 80 meters into centimeters. So we start with 80 meters, times and draw a line. Let's put meters on the bottom and centimeters on top. Centi, as a metric prefix, means 1/100th of the base unit. So 1 meter is larger than 1 centimeter. How many centimeters are in 1 meter? 100 centimeters in 1 meter. So 100 on top and 1 on the bottom. And if we do the math, our answer is only going to have 1 sig fig because the number 80 does not have a decimal at the end. 80 times 100 is 8,000. So with no decimal at the end, our answer is 8,000 centimeters, and this is only 1 significant figure. Number 8 is asking us to read the equipment and record the appropriate volume. So we have 4 different pieces of equipment. Let's start with the first one. Every line that is printed on that particular instrument is worth 1 milliliter. The liquid level is between 62 and 63. So our answer is going to be estimated to the 10th place, I chose to say 62.5. You might have said 62.4 or 62.6, and that's fine. Our next measurement, it looks like the liquid level is on the line exactly, but every line is still worth 1 milliliter. So we are not in between 25 and 26. I think we're exactly on the line. We cannot just say 25. We still have to go to the 10th place, so it's going to be 25.0 milliliters. The next piece of equipment is more precise. Every line is worth 1/10 of a milliliter. Therefore, we estimate to the 100th place. So 2 decimal places in our answer. The measurement is between 19.8 and 19.9. So I estimated 19.85. You might have said 19.84. That's fine. But the final digit is in the 100th place. And our last measurement is similar in that every line is worth 1/10 of a milliliter. If we think it's exactly on the line at 31.3, I still have to add a 0 to show that it's on the line. So I said 31.30. If you think it's just under the line, that's fine. You might have said 31.29, but you had to have a 2 decimal place answer, with a 100th place being your estimated digit. All right, so this following passage applies to questions 9 and 10. So we have 4 different laboratory groups, and they were instructed to determine the boiling point of methanol, and they each did 4 trials. Let's take a look at the results of group number 1. 72, 58, 68, and 62, that data is not precise because those values are not close together. The same problem with group 2. 66, 52, 62, 56, those numbers are too widely scattered. They are not precise. So group 3 and group 4, those numbers are close together. So they are both precise, but only one of them is accurate. So the accepted value for the boiling point of methanol is 65 degrees. So the data from group 4 is both precise and accurate because the numbers are close together and they are close to 65, the true value. Group 3 is precise, but because 59 is not close enough to 65, it is precise but not accurate. Number 11. A student records measurements of mass and volume for a sample of metal. The results are shown above. According to the rules, for calculations involving significant figures, how should the calculated value for the density of the metal sample be reported? Now suppose you forgot the formula for density. Take a look at those units, grams/milliliters. That means grams divided by milliliters. So these units tell us that density is equal to mass divided by volume. So if we take a mass divided by a volume, we are dividing. When multiplying or dividing, you round off your final answer based on the measurement that has the fewest number of significant figures. So in our situation, we have 67.90, which has 4 sig figs, divided by 9.3 milliliters, which has 2 sig figs. Our calculator gives us 7.301075 grams per milliliter. How should we report this answer? Well, the final answer should have 2 significant figures, so the correct answer is 7.3 grams per milliliter. Number 12, consider the 3 objects X, Y, and Z whose masses are listed in the table above. Which of the following has correctly listed these objects in order of increasing mass from smallest to largest? Let's start with object X. Now we remember from our knowledge of the metric system that there are 1,000 milligrams in 1 gram. And we have, for centigrams, there's 100 centigrams in 1 gram. and then there's 1,000 grams in 1 kilogram. So these will help us with objects X, Y, and Z do conversions. To get them all into grams, that would be a nice way to compare them. So 7 times 10 to the 3, or 7,000 milligrams, is what we have for object X. 7,000 milligrams, convert that into grams by dividing by 1,000, and we get 7 grams. So object X weighs 7 grams. For object Y, 8 times 10 to the 3, that's 8,000 centigrams. When we convert, we divide by 100, and we get 8,000 divided by 100, that's 80 grams. Object Y weighs 80 grams. And finally, object Z. 9 times 10 to the negative 3, that's 0.009. To convert that into grams, we're going to be multiplying by 1,000. So 0.009 times 1,000 gives us 9 grams. So now that we know the mass of objects X, Y, and Z in grams, the smallest mass is X, the largest mass is Y. So the correct answer to number 12 is B. In number 13, each of the following calculations requires you to write 2 conversion factors. Each of your conversion factors should be clearly labeled with a number and a unit on both sides of the horizontal line. Make sure that your final answer has a unit. Make sure your final answer is expressed with the proper number of sig figs. And expressing your answer in scientific notation may be convenient in some cases. So we come to part A. The density of lead is 11.34 grams per milliliter. So what should we do when we see a number followed by 2 units? So grams per milliliter, what does that mean? Well, this can be used as a conversion factor because it involves 2 units. This might not be the best place to start when setting up this problem. If I need a conversion factor, I can either write it with grams on top and milliliters on the bottom, or I can flip that conversion factor upside down. Let's keep reading and see what other numbers there are available. Well, it says 2.1 kilograms. This is a good value to begin with because it only has 1 unit. So we start with 2.1 kilograms. So we know that this will involve 2 conversion factors. We are asked to calculate the volume of this lead sample in units of milliliters. So our job is to get from kilograms to milliliters in 2 steps. First, we're going to put kilograms on the bottom, and then we have to get to some other unit. So what should that other unit be? Considering that the density of lead has grams and milliliters, let's first convert from kilograms to grams, and then we'll convert from grams to milliliters. Now, to go from kilograms to grams, we have to know that relationship. We have to know what the metric prefix kilo means. It means that there are 1,000 grams in 1 kilogram. So we put a 1 on the bottom next to kilograms and 1,000 on top next to grams. Now remember, 11.34 grams for every 1 milliliter. That means that 11.34 goes on the bottom next to grams and 1 milliliter on the top. Okay, we're almost done. We have to do the math. So what is the math? That's going to be starting with 2.1 times 1,000 and then divided by 11.34. And if we do this math on our calculator, we get 185.1852, and the number just keeps going, but we have to consider the number of significant figures in the first measurement, which was 2.1 kilograms. Now, since that number has 2 sig figs, then our answer should have 2 sig figs. How do we round 185.1852? How do we round that to 2 significant figures? It's going to become 100, not 180. We have to round up, so it becomes 190 milliliters. And there is no decimal at the end of the number. that number has 2 sig figs. Okay, on to the next question, part B. The molar mass of carbon dioxide, CO2, is 44.01 grams per mole. Again, we see 2 units with one number. So this can be used as a conversion factor because it involves 2 units. You might write grams on top and moles on the bottom, or write that upside down. So not a good place to start. Let's keep reading. It says that the sample has 0.0341 moles. So that is a good value to start with because it only has 1 unit. Let's start with 0.0341 moles. We know we have 2 conversion factors, and it says calculate the mass of this CO2 sample in units of milligrams. So our final answer will be in milligrams. Now let's put the units in the first conversion factor. Moles on the bottom. And what are we going to first convert moles into? Well, it says 44.01 grams per mole. Let's convert moles into grams using that information. And then let's go from grams to milligrams. So how do we go from moles to grams? Well, we have the information, 44.01 grams for every 1 mole. The second conversion factor, we have to know what the prefix milli stands for and what it means. So milli is 1,000th of the base unit. There are 1,000 milligrams in 1 gram. So 1 on the bottom and 1,000 on top. So we're almost done. We have to do the math, starting with 0.0341 times 44.01 and then times 1,000. If we do this on our calculator, we get an answer of 1,500.741, etc. Let's talk about significant figures. Our given measurement, 0.0341, has exactly 3 sig figs because those first 2 leading zeros don't count. Our answer should also have 3 sig figs. Now, how do we do this? How do we round this number to exactly 3 sig figs? Expressing your answer in scientific notation may be convenient in some cases, and it will be convenient now. Because watch what happens when I try to round this. If I said 1501, well, that would be 4 sig figs. If I just said 1500 with no decimal, that would be only 2 sig figs. If I want exactly 3 sig figs, I must write this number in scientific notation, 1.50 times 10 to the 3rd power. That is the correct answer with the proper number of sig figs. Okay, on to our last question on the practice quiz, number 14. The accepted value for the molar mass of magnesium is 24.30 grams per mole. A student did an experiment to calculate the molar mass of magnesium, and based on the laboratory data, they got 21.73 grams per mole. So the percent error equation looks like this. Percent error is experimental value minus accepted value, divided by the accepted value, and then times 100%. And those are absolute value bars, those vertical lines. So the difference between 21.73 and 24.30, so the absolute value of that difference, divided by the accepted value, 24.30, and then times 100%. So if we do this math on our calculator, we get a difference of 2.57 when we take the absolute value, so we ignore the negative sign, divided by 24.30 and then times 100. On our calculator, we get 10.5761, but it said round off your final answer to the nearest 0.1%. Let's call this 10.6% error. All right, well, that was the last question on the practice quiz. I hope that these answers and explanations were helpful. Thanks for watching.